So last time we started working with our Laplace transform. It's this wonderful machine where you plug in a function, f of t, and you get out a new function, f of s. Now, the way it's defined is for the function f of t, you do the integral from 0 to infinity, e to the minus st f of t dt. And of course, that depends on s, because there's this parameter s. Now, the good news is we almost never use the definition. Instead, we develop rules. And from last time, we had a collection of rules. So things like, how do you take the Laplace transform of exponentials, or powers of t, or sine or cosine? And we have this cool rule that says, oh, multiplying by an exponential really is a shift of the output. And we're going to get more rules. Now, we'll start with a quick rule about a function called the Heaviside function. And then we're going to do some practice with Laplace transforms, practice with inverse Laplace transforms, and then we'll get to solving differential equations. It's going to be a lot of fun. So let's get going. So let's meet what's called the unit step function, or the Heaviside function. And what does it look like? Well, if you were to graph this, it has the following shape. Namely, initially, it's 0. So it's 0, and then it jumps to 1. Okay? So that's the function. Now, when I first learned about this function, I thought, what a great name! Heaviside. That's the Heaviside. It's so heavy on the right-hand side. And then it turns out that's not why it's called the Heaviside function. So Heaviside was the name of the mathematician who explored this. Now, of course, this is not necessarily the first mathematician who found these things. So rarely does the first mathematician get the proper credit. But okay, why do we like this function? Well, the thing that makes this function really good for us is we're going to think of this function as an on-off switch. So you say, well, look, 0 is off, 1 on. And so we're going from off to on. And so that's why I like to call it an on-off switch. And so, okay, great. So this will be very useful as we go on in terms of piecewise functions. Because piecewise functions, you have different behavior. And so you can think of different behavior as you're saying, oh, I have something turning on, and that changes my behavior. We'll get more into that in the future, but for now, let's find the Laplace transform. Okay, so Laplace transform of u of t minus a. Now, to be clear here, what does this mean? Well, what this means is now, instead of turning on and off at 0, we're going to turn on and off at a. So our function has a slightly different look. It's been shifted over. So we say, okay, so we're going to shift. All right, now let's begin. Well, there's nothing on our table that looks like Heaviside yet. So what do we do when it's not on our table? We go back to definitions. So the Laplace transform, u of t minus a, is, by definition, integral 0 to infinity of e to the minus st times u of t minus a dt, right? Because whatever we're plugging in, that's what goes in that slot. Now you say, well, hold on, I know what happens. Before a, this is 0, then after a, it's 1. It's really saying there's two behaviors, so we can break the integral into two parts. Namely, what happens between 0 and a, and we say, well, between 0 and a, u is 0. And then what happens from a to infinity, and between a and infinity, well, we say, well, that's fine, u is now 1. Okay, so for piecewise functions, when we're doing Laplace transform, break it up into pieces. And all right, well, one of these two integrals is pretty quick. The first one, right? 0 goes away. Life is good. Life is wonderful. What about the second integral? That's not bad either. What happens? Well, what do we have? The integral of e to the minus st. Well, again, we're integrating with respect to t. So minus s is a constant. So it'll become minus e to the minus st over s, right? Divide by minus s, so there's a minus in front and an s downstairs. And then evaluate a to infinity. Now, as before, what will happen when we let t go to infinity? You'll get exponential drives to 0. So this is 0 subtract, and then plug in a. Well, it's not 0, it's a, right? So you're going to have minus e to the minus sa over s. Or minus minus makes a plus. And I'll put the a in front, because right now we're thinking of the s as the variable. All right, and that's the rule. That's the rule. Now, this is really kind of interesting here, and we're going to drive this point home more in a future time, when we're going to really dig into piecewise functions. But for right now, I just want to point something out here, is we have an exponential function showing up on the right-hand side. We've already seen that when you have an exponential function showing up on the input, it results in a shift. Now here, on the other hand, we had a shift, and it resulted in an exponential function. And it's like, whoa, that kind of feels like symmetry. And that's a good intuition to have. So, all right, great. Well, let's try this out on something a little more interesting. So let's find the Laplace transform of the following function. It's a piecewise function. Namely, it's 0 from 0 to 1, or if we're above 3, it's 3 from 1 to 2, and it's 7 from 2 to 3. Now you might say, wait, hold on, what happens below 0? And the answer is, we don't care, right? We mentioned this last time, but it's always good to remind ourselves we only care about the function f of t for t greater than or equal to 0, because the Laplace transform has that integral starting at 0 to infinity. So okay, so let's find that we didn't define it below 0. Now, what does this function look like? Well, let's graph it. Okay, so we'll have time 0, 1, 2, 3, and what do we have? Well, we're 0 up to time 1, and then from 1 to 2, we jump up to 3. Okay, so this is 3. Then from 2 to 3, we jump up even more, up to 7. And then from 3 onward, we're back to 0. All right, so there's our bum, 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 boom, bum. All right, so there we go. There's our function, a graphical representation of our function. Now, what do we want to do? Well, we could go through and do it the long way, but our goal is to avoid that. And indeed, we're trying to develop the skills to avoid having to go to the definition as much as possible. And so how do we do it? Well, we say, let's use the tools that we have. We've just discovered the Heaviside. We should think of that as an on-off switch. And so we say, okay, let's use our on-off switch. Now, how does one do that? Well, we say, look for where behavior changes. And we say, well, we have some changes of behavior at 1, at 2, and at 3. All right, so what do we do? Well, we say, let's see how we start. Okay, so we start, our f of t starts as 0. All right, now we say, oh, time 1. So that's the change in behavior. So I say, okay, I'm going to have something happen at time 1. Now, what should happen? Okay, so here's the idea. What I want to do when I want to turn something on, but I also want to turn something off. So the way I like to think of this, and again, we'll do this in more detail in a future lecture, but I'm going to take u of t minus a. So this is at time a. I'm going to say what happens after t equals a. That gets turned on. Subtract what happens before t equals a. That gets turned off. So plus on, minus off. So in our case, after 1, we're at 3. Before 1, we were at 0. So I'm going to have 3 minus 0. Okay, then I say, all right, that's that part. And now, okay, next point is 2. So plus u of t minus 2. Say, well, what's happening after 2? And when I say after 2, I mean right after. Not like way after, right after. So after 2, we're 7. Before 2, we're 3. So turn on the 7, turn off the 3. Then finally, u of t minus 3, that's our last place where we change behavior. We say, okay, what are we after? We're 0. What are we before? We were 7. So 0 minus 7. All right, and that's our last piece there. All right, good. Now, the casual observer will say, ah, Steve, I think this works, but I think some of your points are wrong, right? You know, which point should be filled versus unfilled, where we have things come together. Well, okay, so technically, it's not quite f of t, because you might have something just off at the gluing points. But here's the beautiful thing. You don't need to worry about gluing points. Now you might say, well, how do you know that? It says it right there. Okay, cool. Calm down, Steve. Calm down. No, actually, the reason is when we're doing these integrals, what happens at a single point will not, change the final answer, because the changing your function at a single point doesn't change the integral. So that's why we don't need to worry. Okay, so what do we have at this point? Well, at this point we can say, okay, our function we've now written in, if we clean it up, that's 3 u t minus 1, and 7 minus 3 is 4 u t minus 2, and 0 minus 7 is minus 7 u of t minus 3. So that is to say, hey, we can write our function in this nice one-line notation with some on-off behavior. So if we want to find the Laplace of f of t, well, that's the same as the Laplace of our 3 u t minus 1 plus 4 u t minus 2 minus 7 u t minus 3. Now we say, hey, but Laplace is nice. It breaks up. So we can say, okay, the 3 comes out, and then Laplace u of t minus 1 plus 4 Laplace u of t minus 2 minus 7 Laplace u of t minus 3. Right? It's linear. We can break up over addition or subtraction. We can pull constants out. And then we say, hey, we just found that formula. Or if we forget, we just do what we will get used to doing. We grab our sheet and say, hey, I know how to do t minus a, e to the minus as over s. So in this case, what do we get? We'll get 3. This will be e to the minus s over s, because here a is 1, plus 4 e minus 2s over s minus 7 e minus 3s over s And we're done. That's our answer. All right, good, good. And if you like this, good news, we're going to do it a lot more in the future. And if you don't like it yet, good news, you have plenty of time to grow and get to like these kinds of problems. So let's do some practice of doing the Laplace transform. Now, what does it mean to do the Laplace transform? You'll have an expression, and the goal is to say, let me make this look like something I know. We always want to avoid going back to our definition. So the punchline is we have our table. We say, okay, here's our table. How can we make it look like things on our table? All right, so that's our goal. Make it look like things on our table. Okay, so let's get into it. All right, let's start with our first one. Now, the first thing we can say is, look, we have addition. We can break things up. And so we can say the Laplace of 6 plus 5 e to the 2t plus t cubed e to the 4t. Well, that's the same as 6, the Laplace transform of 1, plus 5, Laplace transform e to the 2t. And then, well, just the Laplace transform of t cubed e to the 4t. I'm going to put that e to the 4t in front of the t cubed just to help us sort of recognize our rules. All right, so this is linearity. Let's use our linearity. And we start thinking, okay, do we have rules? Well, 1, yeah, we can think of that as t to the 0, which is 1 over s. All right, that's great. E to the 2t, no problem. 1 over s minus 2. Cool. How about this? E to the 4t t cubed. Well, the t cubed we can handle. T cubed would be what? 3 cubed, which is 6, over s to the 4. But what happens with this e to the 4t? Well, that's our rule. If we multiply by an exponential, we have a shift. Shift by 4. So sometimes I like to make notes because it's easy for me to get lost. So I would say, look, normally the t cubed would be 3 factorial over s to the 4. And then I say, oh, this is going to shift. So s becomes s minus 4. Okay, good. Now the rest of these rules we already mentioned. We know what to do. So we get 6 times 1 over s. We'll go ahead and write that as 6 over s. Plus, we have 5 times 1 over s minus 2. So 5 over s minus 2. And then here, we say, okay, 3 factorial. That's also a 6. And now, instead of s to the power 4, we're going to be shifting by 4. So it's s minus 4 to the 4. And there's the first one. Done. Done with that one. Okay, well, that was a good warm-up. Now, let's go to the next one. All right. So, what do we have? Well, we have Laplace transform of t squared plus 10 sine of 4t cosine of 4t. Okay. Now, before we break up, let's just scan, and we say, Okay, t squared, no problem. T squared, n equals 2. 2 factorial over s cubed. We can handle that. That's fine. But notice this is multiplying. We don't have any rule yet for multiplying other than this e to the ct. So we're getting into a little bit of like, careful here. But there was this tip. Do you remember that? It was when finding the Laplace transform, look at ways to rewrite in terms of functions we already know. So in other words, when we talk about functions, we know functions in here. So we say, okay, well, right now we're kind of stuck. But we start saying sine, cosine, there's identities. And is there a good one for us? Well, there is a wonderful identity, namely the following that says sine of 2 theta is 2 sine theta cosine theta. So, we say, okay, we have a sine cosine, the insides match, so we could say, all right, so if we had 2 sine of 4t cosine of 4t, so I added 2, according to the rule, that would be sine of 8t. So we say, aha, because 10, true story, is 5 times 2. So we're like, yes, good. If we can convert it, then we'll say, all right, down to just a single sign. And now, once we see the sign, it'll open up our eyes, and we'll be able to carry it out. So cleaning this up, rewriting this, Laplace transform of t squared plus 5 sine of 8t. Okay, now we're doing good. So this is Laplace transform of t squared plus 5 comes out, Laplace transform of sine of 8t. And these are on our formula sheet. Okay, so we have the first one, 2 factorial over s to the 2 plus 1. Now, on this one we have the 5, and for sine, well, it's s squared plus the inside, 8 squared, then the top is that inside number. So you have to be careful, is it 8 or the number? It's sine versus cosine. Read your table. You don't have to memorize it. The goal here in this part of the course is not to be like, memorize the table. No. Learn to use the table. All right, 2 factorial is 2. 5 times 8 is 40. So 2 over s cubed, 40 over s squared, plus 64. And there we go. Great. So now we have practice finding Laplace transforms. And you're going to get a lot of practice. You're going to become pretty good at this over the next few weeks. So let's try doing inverse Laplace transforms. And again, similar tip. When we're looking for inverse Laplace transforms, look for ways to rewrite in terms of functions we have seen. In other words, look for things in the table. Now, I want to pull up the table again because I love a good table. Who doesn't love a good table? Okay, so here's our table. Now, when we talk about using our table, remember that every rule for Laplace transforms is associated with the rule for inverse Laplace transforms. And I want to just go ahead and write down the rules explicitly. Oftentimes, they're not written explicitly, but I want to get to the point where it's like, yes, I see what's written, and I know that there's actually a rule written there, or at least there's a rule implied. So, when we do this, we would say the inverse Laplace of 1 over s minus c. Well, what is that? It's e to the ct. Okay, the inverse Laplace of n factorial over s to the n plus 1 is t to the n. Isn't this easy? It's almost like you're basically just copying, because you're basically just copying, right? The only thing that you're doing is you're just saying, okay, you're just putting inverse Laplaces here where you just had Laplaces there. Okay, so the punchline here is when we're looking for inverse Laplace, we're really thinking about look like these kinds of things. So these are the things that we're going to be really good at using inverse Laplaces of, because we have a chance, a real chance. All right, b over s squared plus b squared. That's sine of bt. Now this one, of course, this is an important one. If we ever say, oh, I see a function I'm used to, but I see it's been shifted, then that tells me that it's the function I thought it was, but I'm going to multiply by an exponential. Okay, so those are the inverse Laplace rules. And so our goal when we're taking inverse Laplace, try to make it look like these things so that we can apply the rules. So, getting back to our problems, say, okay, what does this kind of look like? Well, we say it looks a lot like this part here, n factorial over s to the n plus 1. Notice here I have n is 2. So I'm going to try to fit this mold. Okay, so for reference, I'm going to make a note for myself that says, well, this looks most like the following, namely the inverse Laplace of 2 factorial over s to the 2 plus 1 is equal to t squared. Okay, so that's in the background. Okay, so what are we going to do? Well, our goal is to make that look like that as best we can, as best we can. Now, there's some subtleties here, namely this 2. It's not just s, it's 2. So how do we handle that 2? Well, okay, so the inverse Laplace of, we'll have 80 over 2s plus 1 cubed. What we can do here is we can say, well, we can pull this 2 out, and we'll do it slowly so that we can see what's happening. So think of it as 2 times s plus a half, and we have cubed. I say, okay, so 2 cubed is 8. So inverse Laplace of 80 upstairs over 8 times s plus a half cubed. Okay, so we're making progress. 8 goes into 80 10 times. So this is inverse Laplace of 10 over s plus a half cubed. So we're getting close, we're getting close. Now, what do we want upstairs? We want 2 factorial, which is 2. What do we have? 10, which is not 2. So what do? Well, we say, okay, if I just want 2, I have 10. I have basically a factor of 5, because it's a true story. 10, it turns out, this is 5 times 2. And now we can say, pull the 5 out. Say, all right, good. So we now have 5 inverse Laplace of 2 over, now s plus a half. I'm going to write that as s minus a half. And instead of 3, I'm going to write it as 2 plus 1. Okay. Now, you might say, why did you choose to do that? Well, because we don't have s to the 2 plus 1. We have s minus something. See, we have a shift. Okay, so we have a shift by minus a half. So we say, oh, okay. All right, so that's good to note. So when we see here's a shift by negative a half, that tells us that we're going to have an e to the negative 1/2 t involved in our answer. All right, so all together, what do we have? Well, we have the 5, then we have the shift, so we'll put that in, e to the minus a half t. And now, after you take account of the shift, think about it as if there were no shift. So it really would be like 2 over s to the 2 plus 1. Say, oh, well, that's t squared. And that's the answer. Okay, so that's that one. Now, that takes a while to get used to, right? So I wanted to make sure we get what happened. Okay, the 5, no surprises. The shift by minus a half, okay, that introduces an exponential function. And this idea of like, after you account for that exponential function, ignore the shift, right? It's like the shift has already been accounted for. So it's like you can cover it with your finger. You say, oh, it's like 2 over s to the 2 plus 1. That's what I mean to say, okay, once you know how you've got the shift accounted for, to figure out the function, then you figure out your rule, as if there were no shift. All right. Well, all right, that one is done. How about the other one? Now, s minus 1 squared plus 16. Okay, now, there's not a lot you can do with that denominator. That's as good as you're going to get. You're just no hope to make it cleaner. Okay, so what can we do? Well, it's actually not bad, right? It's like s squared plus 16, except there's been a shift. And so the idea says, okay, well, let's stick with that s minus 1. We like the s minus 1. So we're saying, okay, what we want to do is we want to make the numerator, the upstairs, make that also look like s minus 1. Okay, so let's do that. And let's see where that takes us. So we have our Laplace inverse of, well, downstairs, it's as good as you can hope for. So I'd like it, instead of s, I'd like it to be s minus 1. So what do? You make it s minus 1, right? Yeah, exactly what you do. So you say, okay, 9 times s minus 1. And now at this point you're saying, oh, Stephen, I don't know. Well, okay, well, what's wrong? Well, because that's 9s minus 9. You're right. We need to fix that. So after you make the change, you put in a fix. So to get to 9s minus 7, and here's 9s minus 9, you add 2. So this goes back to your algebra, learn how to rewrite things. A lot of what we're doing in this phase of the course is practicing algebra, where we're learning to rewrite things in the right way. And by the right way, we mean where the table comes into play. All right, now what can we do? Well, what we can do at this stage is say, okay, let's break it up. And we like to have okay, let me take a step back here. I'm getting a little excited, of course. Who doesn't get excited solving a good problem? Because we see this s minus 1, we see that there's a shift by 1. And so we know that e to the t is going to play a role in our answers. So that's why when we see an s minus 1 downstairs, you always want to make sure that there's a matching s minus 1 upstairs. The s minus has to be consistent over the whole thing. So we're going to break this into 2 parts using a beautiful fact called addition. And also because we have the upstairs. It's so much easier to break things up when things are upstairs. Breaking things up when they're downstairs, not fun. Okay, so we have 9, because we can pull out constants, s minus 1 squared plus 16. Now I'm going to pause. 16, also known as 4 squared. Yes. Plus, and here I'm going to pull out a 2. I might regret it in a second, but that's okay. And then we're going to have 1 upstairs and s minus 1 squared plus 4 squared. Okay, now we go back to our tables. All right, so we already know, because we're seeing s minus 1, we're going to have e to the t's. So for now, imagine that you squint for a second and say, okay, if there weren't any s minus 1s, what would you see? Well, all right, so our s minus 1 is going to be a shift which means we have an e to the t. So now replace s minus 1 by s, you get s over s squared plus 4 squared. And we say, does that show up anywhere on our table? And it does right there. S over s squared plus b squared says, oh, this should be a cosine of 4t. Okay, good. Now, similar thing is going to happen here. Again, we see an s minus 1. That's saying that we've done a shift, which says, okay, e to the t is going to be involved in our answer. Now, imagine that there wasn't an s minus 1. That was just s. What do we have? 1 over s squared plus 4 squared. Now, does that show up on our table? It's really close to the sign, but not quite. What's wrong? The 1 upstairs. You see, it should be a b over s squared plus b squared. Here, b is 4, not 1. How do we fix it? Well, the answer is we make it a 4, right? So whenever we say, oh, how do we fix it? The answer is we just fix it and then deal with the consequences. Normally the consequences aren't too bad. So we say, okay, we make it a 4. Great. All right. But wait, if I put a 4 here, I have to compensate. So what's the compensation? If I put a 4, I should also have a 1/4, which then can be pulled out, so I can put it over 4. So these 4s are canceling. And now we're like, oh, good. With that in place, that tells us that, okay, this should be a sine of 4t. So we're now ready to write our answer. We have the following. Namely, we have here our 9, our e to the t because of the shift, and cosine 4t. 2 over 4 is a half. Again, our shift, so we have an e to the t. Whoops, sorry about that. And then sine of 4t. And there we go. There we go. That's it. That's the answer. Ah, lovely, lovely. All right. And of course, it's really a matter of getting used to the table, writing things. Either, do I look at Laplace transform or do I look at inverse Laplace? How do the expressions look? How do you piece things together? Okay, shifts, that means exponentials. But, okay, what was the rest of the function if I didn't have a shift? And with practice, it becomes second nature, and it will help you make it more automatic. That's our goal. Make it automatic. So keep practicing, right? And we still have more stuff to do. So let's keep going. So if we're going to get to the point where we can use Laplace transforms to solve differential equations, we need to get an understanding of how Laplace transforms works when we apply it to a derivative. So let's do that. So, all right, what's the Laplace transform of f prime? Okay, well, if we don't know, we say go to the definition. So we have integral e to the minus st f prime t dt. We say, well, okay, f prime t, we know how to integrate that, and we know how to differentiate an exponential. So, all right, when we integrate with the f, so that's our f of t, e to the minus st. And then, okay, integral f of t, take a derivative, minus s comes down. All right, well, what do you have? Well, when we evaluate, again, as t goes to infinity, the exponential drives us to 0, which is good. And at 0, we have e to the 0 and f of 0. So that's where that minus f of 0 comes in. Plug in at 0. Remember, we're subtracting the lower bound. Here, the minus s comes out. You have a plus s. And we say, well, wait, that looks really familiar. That's the Laplace transform of f of t. So what's the punchline? The punchline is taking the Laplace transform of a derivative is like multiplying by s. That's great. We like that because that's like an algebra thing. It says, oh, derivatives are add algebra stuff to your Laplace transform. Like, woohoo, algebra, algebra. Now that's one derivative, but what about second derivative? Well, it's a rule so nice, we can apply it twice and say, okay, so if I think of the second derivative, it's the derivative of the first derivative. So I'm applying this rule to the first derivative. All right, so it's S, Laplace transform of f prime of t minus f prime of 0. And now, again, apply the rule. So you get S times all of this, S Laplace transform of f of t minus f of 0 minus f prime of 0. Or S squared Laplace transform of f of t minus s f of 0 minus f prime of 0. And you can repeat. And in general, we have that if we're looking at the nth derivative, we'll have s to the power n times Laplace transform as if there was no derivative, and then extra stuff. Now, I just want to point out, what are these things? What do we see here? Well, what we're seeing here is that these extra pieces all have something in common. These are initial conditions. And so one of the cool things about Laplace transforms, and we'll see this as we get going just a second here, is that it's sort of the opposite of what we've been doing in other cases. So when we've been solving differential equations before, we sort of get to a certain point, we say, okay, we now have a general form, and plug in and solve initial conditions. So in other words, initial conditions come at the end. With Laplace transforms, we move the initial conditions and say they're going to come in at the very beginning. And so that's a very different thing that happens here. So the initial conditions come in at the start. And we'll make this more clear as we go through and do some examples. But all right, let's try these rules out. So suppose we have x double prime plus 2x prime minus 15x is e to the 2t sine of 5t. And we know what happens to x at time 0, it's 3, and x prime at time 0 is 1. And we're after x of s, which is the Laplace transform of x of t. Well, we say, okay, what can we do? We could solve this differential equation and then run it through the Laplace transform. However, I don't think that's the point here. The point is to say, let's use our tools. And so what are our tools? Well, we have Laplace transforms. So, okay, let's start there. So, two things are equal, and if two things are equal, that says that when we put them into the machine, and the machine being the Laplace transforms, those will be equal. So we can say Laplace transform of x double prime plus 2x prime minus 15x is equal to the Laplace transform of e to the 2t sine of 5t. All right, so we're going to be going off of that. Now, we have to work with these two sides. And on the left-hand side, well, we can, of course, use linearity. Laplace transform of x double prime plus 2 Laplace transform of x prime minus 15 Laplace transform of x. All right, well, we'll work on that. We know a few things. We know this capital X, that's Laplace transform of little x. Okay, well that's fine. What's the Laplace transform of x prime? Well, that goes back to what we just talked about. And so if we pull back, say, hey, what's happening here, x prime, it'll be s Laplace transform of x minus x0. All right, so this is the same as s Laplace transform of x minus x0. Or if you like, we know that this already has a name. It's s times x minus x0. And in a similar way, Laplace transform of x double prime, we apply the rule to be s squared Laplace transform of x minus sx of 0 minus x prime of 0. Or if you like, s squared capital X minus sx of 0 minus x prime of 0. Okay, so we have those facts in the background. So we say, great, now let's use those. Say, okay, so according to our rules, we have that this will be, the first one will be s squared capital X subtract s times x of 0. But x of 0 is 3. So subtract 3. Just subtract 3. Sorry. I was like, wait, what? Subtract 3s. No, yep, I was right. There we go. Sorry about that. Yeah, you have to keep track because there's some. Notice the powers of s. S squared, s1, right? s1. And so the powers of s go down. Okay, so we have subtract 3s minus a minus 1 makes plus 1. Plus 2. Okay, Laplace transform of x prime. Okay, that'll be s capital X subtract x0, which is 3, and then minus 15. Laplace transform of x is capital X. All right, good. So, well, what do we have? We can gather the terms with x. Then we have s squared plus 2s minus 15, right? S squared, 2s minus 15, capital X. And, okay, we have a minus 3s. And here's a plus 1 minus 6, right? 2 subtract 3 minus 6, so that's minus 5. And this is, by the way, one of those times when it's like, okay, know how to differentiate your 5s from your s's. Let's pause for a second here. Do you see s squared 2s minus 15? Does that look familiar? X double prime, 2x prime, minus 15x. It feels like what you would do with characteristic polynomials, doesn't it? Because it's what you would do if you had characteristic polynomials. It's not a coincidence. We keep seeing these same things over and over and over again. And hopefully by now we're like, yeah, we're really used to these kinds of things. All right. Now that's the left-hand side. The right-hand side, the e to the 2t, this is a shift, right? So what's going to happen is s is going to go to s minus 2. The sine of 5t, if we just see sine of 5t by itself, well, that would be a 5 over s squared plus 5 squared, which is 25, right? b over s squared plus b squared. So that says that the right-hand side becomes 5 over s minus 2 squared plus 25. All right, let's rewrite all of this. So what do we have? At this stage, we have the following. We have s squared plus 2s subtract 15 times capital X subtract 3s minus 5 is equal to 5 over s minus 2 squared plus 25. Now, what's our goal? Our goal is to find capital X. And the good news is we just have one of those. So it's great. So you just have to isolate that one. Okay, so we'll move stuff across. We can say s squared plus 2s minus 15 times x. Well, that's 5 over s minus 2 squared plus 25 plus 3s plus 5. That's a 5 there. And now divide. So capital X is equal to And, well, we'll go ahead and divide each term. We'll think of this as s minus 2 squared plus 25, and then times that by s squared plus 2s minus 15, and then add 3s plus 5, and divide that by s squared plus 2s minus 15, and lo and behold, we're done. Now, could we simplify? Yes, but that's not the goal for today. When would we simplify, or what would we do? Well, we could, for example, try to say, well, maybe if we could pull it apart, maybe using partial fractions, we could get it to a space where by pulling it apart, we say all the pieces have a nice inverse Laplace. And if we could get there, we could actually solve for x, little x, the original function we were looking for, the solution to the differential equation. In fact, that's a good strategy. So let's recap that strategy. So, given an initial value problem, it has to have initial value. Laplace transforms do not work when we don't have initial values given. So you need to assume initial values are given. All right, step 1. Take the Laplace transform of both sides. Use the table and rules for derivatives. And we talk about rules for derivatives. These are the main rules that we're going to use. So know how to use your rules. Say, all right, so we take the Laplace transform of both sides. In the process of doing that, we're going to have lots of expression, but because of our rules for derivatives, we'll get down to just x's. Say, okay, great. Step 2, solve for x. Say, okay, I've gone x by itself. Now what? Well, step 3. Now this is a step that takes some time. Simplify the expression so that each term is something that you recognize from the table. All right, once you've gone there, well, what can you do? Well, if capital X is the Laplace transform of little x, then we can say that little x is the inverse Laplace transform of capital X. And what's happened is we've already gotten capital X. That's step 2. We said, by simplifying, we have things that we can do the inverse Laplace of, and therefore we can solve for little x. Life is good. We have our solution to our differential equation. A strategy. So now we see this is why we came. This is why we're studying Laplace transforms. It can help us solve differential equations. So to finish up for today, let's actually go through and run the process. So we're given x double prime minus 6x prime plus 13x is equal to 0. We have our differential equation. We also have initial conditions. X of 0 equals 4, x prime of 0 equals 12. And we're going to solve for x using Laplace transforms. We could have solved for x using other methods. In fact, these are the kind of differential equations we started off pretty early in the course. But we have new tools. Let's use our tools and let's see what happens. Okay, so remember the first step. Run the process by taking the Laplace transform of both sides. So we're going to do Laplace transform of x double prime minus 6x prime plus 13x. And we're going to say that's the Laplace transform of 0. Now we haven't mentioned this before, but what is the Laplace transform of 0? It's 0, right? It's what you think it is. 0, you're a friend. We like you. All right, so let's work on this part right here. Okay, so what do we have? Well, this is the Laplace transform of x double prime minus 6 Laplace transform of x prime plus 3 Laplace transform of x. By linearity, we're pulling things apart. Okay, so after we've pulled things apart, we're going to work on each individual expression. We say, all right, well, here, the second derivative, this is the same as s squared capital X, which is what we're trying to solve for, minus s, and we'll write x of 0 minus x prime of 0. We'll fill these pieces of information in just a moment. Minus 6, parentheses. Parentheses are friends. They save us points, right? Because we want to make sure we distribute through appropriately. So use your parentheses. Save your points. All right. So s capital X minus x0. That's the Laplace transform of x prime. And then plus 3, Laplace transform of x is the Laplace transform of x. Okay, so we'll just mark what we know. X of 0 is 4, so this is a 4. And x prime of 0 is 12. All right, so now we group. Okay, and I forgot to put an equal sign here. All right, so at this stage, we have that, we get the following. We have, for the x, what do we have? S squared x, we have 6sx, and we have 3x. So I'm going to factor out the x, so s squared minus 6s and plus, whoops, I just noticed something. See, I had 13. I've been writing 3. Oh my gosh, that's very embarrassing. All right, let's fix that. Sorry about that. And that's, like I've mentioned in the past, the biggest challenge you have in the course is often copying. So make sure you copy things. Because what I was going to point to is say, oh, don't you recognize these numbers? And I was like, it matches here. I was like, wait, 3 doesn't match. I was like, oh yeah, because I made a mistake. So, all right, so we can fix. S squared minus 6s plus 13. X double prime minus 6x prime plus 13x. Yeah, matches. Okay, we have minus 4s. Okay, that's good. And then we have minus 12. And minus 6 times minus 4 is plus 24. So minus 12 plus 24 becomes plus 12. All right, good. Whew. Okay, so now remember, this is 0. All right, so let's write this all nice and neat on one line. We have s squared minus 6s plus 13 times x is equal to, because I can move these pieces across, 4s minus 12. All right. Now we say, well, that says x is 4s minus 12 divided by s squared minus 6s plus 13. All right. Now downstairs, what can we do? It doesn't factor nicely. 13 is a hard number to work with. And so we say, well, if it doesn't factor, that's okay. We can do other things. We can complete the square. S squared minus 6s. We say, what would we need to add? Divide negative 6 by 2 is negative 3. Square that, comes 9. So we need to add 9. But wait, we have plus 13. No worries. Add 4. 9 plus 4 does equal 13. Okay, so now we say, well, this would make this piece, that's s minus 3 squared. Here, this is a 2 squared. And now we like, ooh, this is really good for us. Because what do you see? We already have s minus 3 upstairs and down. It's like they wanted to give us a nice answer. Well, we're just starting out, right? So they should be nice to us. Maybe in 1 or 2 more lectures are going to be like, gloves are off. Okay, so this is about as good as we can hope for. So now we're ready to go into our final step. There's not much simplifying to do here. So we say, okay, our little x, our solution that we're after, that's the inverse Laplace of big X. Well, that's the inverse Laplace of this expression. 4 times s minus 3 divided by s minus 3 squared plus 2 squared. Now, let's just go ahead and pull out the 4. So we have 4 inverse Laplace of s minus 3 over s minus 3 squared plus 2 squared. Since everywhere that an s occurs, it occurs as an s minus 3, that tells us something. So this s minus 3 here, that's our shift by 3. Well, that tells us that we're going to have our answer is going to involve an e to the 3t. All right, well, that's good to know. What else do we see? Well, now, remove the shift, and after you remove the shift, what do you see? You see s over s squared plus 2 squared. And we say, oh, well, that's on our table. What is that? It's the cosine. So this part here is cosine 2t. And so, putting this together, what do we end up with? Well, we end up with the following. Namely, we'll have 4, the shift makes an e to the 3t, and then cosine 2t. And we're done. We actually solved it. We didn't have to find the roots. We didn't need that. We didn't need to solve for constants, for initial conditions, because the initial conditions come in at the start and they work themselves in just right. And so it's a very nice, very beautiful process to go about and solving a differential equation. Of course, when you have the right kind of differential equations. So this is great. It'll be wonderful to get more practice. So we will, but that'll be next time. So thank you for joining me. Thank you for being patient, and we'll see you again. Bye.